In this video, I'm going to describe how to find the partial fraction decomposition of this rational expression. I encourage you, though, to pause the video and try to work out the problem on your own. If you get stuck, you can watch my explanation to get unstuck, and then maybe pause again and see if you can get a little farther. So the first thing we need to do is identify the form of the partial fraction decomposition. So take a moment and think about that. Perhaps pause the video and try to identify it on your own. The form depends on the factors in the denominator, and for these two linear factors we get a over x plus b over x minus 1 plus c over x minus 1 squared, because that second linear factor is repeated. Next, we need to clear the denominators, and we can do that if we multiply everything by the common denominator, x times x minus 1 squared. Now I'm going to multiply each of the numerators by that, and we could write out that process, or we might be able to just identify that when we multiply this numerator by the common denominator, it'll cancel, and we'll be left with 2x plus 3. Here the x factor cancels, and we're left with a times x minus 1 squared. The b term becomes b times x minus 1, because one of the x minus 1 factors cancel. And finally we end up with simply c times x, because both of the x minus 1 factors cancel. So now we need to figure out what the values of a, b, and c are, and there are two ways to do that. First, let's look at the method of equating coefficients. If we multiply all this out, we end up with x squared minus 2x plus 1 times a plus b times x squared minus x plus cx, which gives us a x squared minus 2ax plus a plus bx squared minus bx plus cx. And then if we gather together all the x squared terms, we see that the coefficient is a plus b times x squared. If we gather together all the x terms, I get negative 2a minus b plus c times x. And finally, the only constant term is just a. So I want to compare the coefficients of x squared and x and the constant with the coefficients on the other side. We notice that there is no x squared term, so I can think of that as having a coefficient of 0. And I can develop a system of equations. First, a plus b equals 0 comes from the x squared terms. Negative 2a minus b plus c equals 2 from the x terms. And finally, a has to equal 3. So this is a pretty nice system of equations to solve, because we can simply identify a right away. A equals 3, which means that 3 plus b has to equal 0, so b has to equal negative 3, and then finally plugging both of those into the middle equation, we end up with negative 2 times 3 minus negative 3 plus c equals 2. And so negative 6 plus 3 plus c equals 2, negative 3 plus c equals 2, so c has to equal positive 5. And so from this process of equating coefficients, we see that the value of a is 3, the value of b is negative 3, the value of c is 5, and we end up with a partial fraction decomposition of 3 over x minus 3 over x minus 1 and plus 5 over x minus 1 squared. Now, the technique of equating coefficients is a very good one, and it's general. It'll work in lots of different situations. But for these types of problems, there is a second technique that can sometimes be a little faster and involve less computation. The second technique relies on the fact that I want this to be true for every possible value of x. So if I choose some convenient values of x to plug in, I might be able to find the values of a, b, and c without quite as much computation. Notice that the zeros of these factors, when x equals 1, this becomes 0, and when x equals 0, the x factor, of course, equals 0. So those are kind of convenient to plug in. If we plug in 1 for x, we end up with 5 on this side, and on the other side, the a factor is going to disappear because it becomes a times 0, as does the b factor, because that'll become b times 1 times 0. And so the only thing that's left is c. So that tells me that c has to equal 5. And if I plug in x equals 0, then this becomes 3. And here I get a times 0 minus 1 squared, and b times 0 times negative 1, and c times 0. So the b and c terms disappear because they have a factor of 0. Negative 1 squared equals just 1, so we end up with a equals 3. And now to find the value of b, we could choose some other kind of nice value for x to plug in. 2 might be a pretty convenient value because 2 minus 1 is just equal to 1. And that gives me 7. 2 times 2 is 4, plus 3 is 7. On the other side, if I plug in 2, I get 1 squared, so I end up with simply an a. Here, I get 2 times 1 times b, so I get 2b. And finally, 2 times c. But I know what the values of a and c have to be, so this is really 7 equals 3 plus 2b plus 10, and solving that equation will give me a value for b. Of course, this is 7 equals 13 plus 2b, so negative 6 has to equal 2b, and we find that b has to equal negative 3. So we end up with the same solution that we did with the original method of equating coefficients, with perhaps a little less computation. We didn't have to set up a system of equations. But again, this technique is a little more specialized, whereas the equating coefficients technique is a little bit more general. So it might apply in other situations where this technique might not. I hope you enjoyed the video. Thanks for watching.